Start recording. All right. So let's see. Where's the theme song? All right. Good afternoon, everybody. We have. Oh, I see. There is a caption um, in the meeting. It is kind of nice. I don't know if it helps. So I found this app online. It's called Snapchat or Snap Camera, and it's very nice. It can change the way I look online to something rather exciting. Like for example, if I turn off this Snap Camera, I have this a typical look of Ajahn Teepanis, but if I put a like Japanese, yeah, it's very nice. This looks like a Japanese a cartoon version, or if you prefer some of very dark level, very nice. Yeah. Maybe you prefer this. I don't know. Um, I think I'm gonna go with the baby face for this lecture, and I hope it's all right. Okay, so like Degen said that Chanita Pa is not feeling so well this week, so she will not be here with us today. Um, So before I begin with the Navier-Stokes equation that we left from the last week, I need to talk about something important about the grade. Let me stop the music a little bit. The thing is, I have to turn in the grade in November 15. Okay, it is here. Are you seeing the calendar on the screen?
Yes,
just to check. Okay, very good. So that is the day I need to know your grade, and that means we have to take a final exam before that, before the 15th. So what do we do? I think it should be this week where I am pointing this mouse over here from the 8th of November to 14. I don't know what date it is. Let's pick.
Do some take-home exam.
Okay, so that is what I want to talk about. What would be the format of the exam that you prefer? I guess there are many options. One option is that it is an on-site exam. You guys come to the department, to the physics building, and you can sit in different room if you like to prevent the COVID. Or we can have a take-home exam. Now the take-home exam, I don't know, for the on-site exam, I can make it the same problem because you guys will not be able to look at each other's answer, but for take home, I guess it'll be different problem for different people, and the way you choose which problem you are going to do, probably using a lottery, can be, or you can choose. I guess you can choose. Maybe you can choose. I don't, which one? Which one do you prefer? So is it all right that you need to take a lottery to choose the problem that you will have to do? It'll be very similar problem for each of you, but at least they are different somehow. Um, And then you don't have the time constraint. You have the entire week to do. And the problem will not be something that you can find the answer on the internet. So it'll be something usually that we talked about in the class. And if you go back to the material in the class, you should be able to do these problems. That's how I will design the exams. I will design the exam such that if you go back to the lectures, the videos, the Google Colab, and PowerPoint presentation, and review those, you should be able to do the exam within 2 or 3 days time. But the problem will not be identical for the three of you. So is that okay?
Okay, Ajahn.
If
We will go
that's
for take-home exam.
yes?
And we will go with the take-home exam, and then we will. Ajahn can just give us the question. It's okay even if you don't do the lottery.
Okay. So I guess I'll give you 3 problems for each of you. It'll be very similar. Um, very good, very good. So let's do that. What about you, um, Patrada? What do you think? Which one do you prefer?
หนูก็คิดถึงเทคโฮมค่ะแต่เมื่อกี้หนูยังแปลไม่ค่อยออกว่าถ้าเป็นเทคโฮมจะเป็นแบบไหน
เพราะถ้าเป็นเทคโฮมก็จะได้ข้อไม่เหมือนกันต่างกันนิดแล้วก็เวลา1 อาทิตย์แล้วก็ปรัชญาในการออกแบบก็คือมันจะไม่เหมือนกับที่คุณสามารถจะไปหาได้ในอินเทอร์เน็ตแล้วก็อันหนึ่งก็คือปรัชญาในการออกแบบว่าถ้าคุณไปทบทวนกันบ้านแล้วก็PowerPoint สไลด์วิดีโอต่างๆก็จะสามารถทำได้นะครับในเวลาสักตั้งทำ2 วัน 3 วันประมาณนี้อันนี้คือที่คุณได้เห็นในเทคโฮมเราจะเลือกอะไรอ่ะ
เลือกเทคโฮมแล้วกันค่ะ
Okay. So I think we are going to go with the take-home exam. Okay, I'll let you know what the time will be like. I can post the problem for you maybe on Monday. Okay, next Monday. This coming Monday. All right. Let's get to the Navier-Stokes equations. This here. What do we do? Well, today I think is going to be probably the last lecture in this series because the semester is ending, and so I don't have enough time to do all of this. So we will have this very short but a good quality lecture on Navier-Stokes equation, right? And how do we actually solve this equation and how you would do it using numerical calculation. Let's go back to the last slide on the previous lecture. So I showed you this Navier-Stokes equation. It's the equation that tells you how the fluid or gases or anything that is flowing behave, okay? Now you can expand this into a full form in 3 equations on 3 axes, the x-axis, the y-axis, and the z-axis. In here we have this component of the velocity. That's Vx, that's Vy, and that's Vz, okay, in the x, y, and z direction. So we have this equation. And I told you that the way we interpret this equation is simply Newton's second laws of motion. But instead of the net force on the right-hand side, we have the force per unit volume, like so. okay, on the right and on the left. So, well, there are fluid can experience many kinds of forces. For example, we can have gravity here on the right hand side. We can have pressure. We can have also this viscosity. And in Thai language, it's called kwam nương. Kwam nương. Okay. So, but in this lecture, I think it'll be a good idea for you to try to solve this equation analytically by hand. You know, because when we, especially for physics students, you didn't have a chance to actually solve this equation before. Let's ask from experience. You know, like D. Chen, right? You are
Yes, sir.
master degree physics student, but did you have you ever solved this Navier-Stokes equation during undergraduate level physics courses?
No, Ajahn.
Okay, so I thought so, but unless you study engineering, fluid engineering, you've seen this before. So let's go with the simple analytical solution of how you do it in general, and then the numerical afterward. Okay, let's focus on something rather simpler. Okay, not 3-dimension, but only in 2-dimension. In this case, we want to solve for the speed, how the fluid flows in the tunnel, in the 2D pipe, so to speak. And I can write the components of that velocity into two symbols. I can use U for the X component and V for the Y component. I also need to know the pressure at every point inside this pipe, inside this channel. Okay, so how do we do it? We begin with this full-fledged expanded form in 3Ds. Now, because the problem is only in 2 dimensions, we can then eliminate the third equation. Okay, that's all gone. So we only have now 2 equations, but then again, we need to eliminate the derivative respect to the z-axis also in the x and the y. You will notice here that you have du dz, that's d dz, that d second dt. Okay, so we have to kill that terms also because we only focus on 2 dimension in this case. Well, what do we do? You will notice that we have 3 unknown. Okay, we have u, the v, and the p. So previously, we only have Navier-Stokes with 2 equations, that one and this one. And that would not be enough for you to solve for 3 unknowns. And that's why we usually invoke or we use this continuity equation, okay, and combine this to get the full 3 equations for this problem. We have this first one and second one and the third one. And that is what we normally do in solving Navier-Stokes equation. By itself, it's not enough to find a solution. We have to have another set of an equation, namely the continuity equation, or in Thai we call that สมการความต่อเนื่อง เป็นสมการที่อธิบายถึงว่าเวลาที่สารมันไหลมันต้องต่อเนื่องไปเรื่อยๆนะครับหรือถ้าจะเป็นพูดเป็นแบบกฎอนุรักษ์ของมวลก็ว่าได้นะครับมวลเนี่ยเวลาที่มันไหลเนี่ยมันต้องไหลจากที่หนึ่งไปยังที่หนึ่งมันไม่สามารถที่จะมาผุบโผล่ออกมาจากที่ไหนก็ได้มันต้องไหลมาจากสิ่งแวดล้อมเท่านั้นนะครับ So we need to use both Navier-Stokes and the continuity equation to solve for fluid dynamics. Okay, so with that, what do we do next? Let me put the problem in a precise detail. And here I have this X direction, I have the Y direction, and I know that the length of this pipe, of this channel, is 2h, okay, because the middle line is at 0. You go up by h and you go down by h. So the length of this pipe, of this channel, is 2h. Again, you want to solve for the velocity and the pressure. Now, to find the solution, you need to make a lot of assumptions here, because without these assumptions, it'll be very complicated to do so. So let's go with the first assumption, steady state. What does it mean? It means that the system does not change over time. Well, that is not really true for all kinds of flow, but normally when the system goes to equilibrium and everything's freeze, things becomes equilibrated. So we are assuming that the velocity and the pressure does not change over time. Okay. ในเงื่อนไขข้อนี้เราจะสมมุติว่าความเร็วตอนแรกๆที่มันไหลมันอาจจะมีการกระเพื่อมต่างๆนะครับซ้ายขวาซ้ายขวาแต่พอมันเข้าสู่จุดสมดุลที่เป็นสภาวะที่ไม่เปลี่ยนแปลงกับเวลาแล้วมันไหลอย่างต่อเนื่องไปเรื่อยๆไม่ขึ้นอยู่กับเวลานะครับอันนี้เรียกเป็นภาษาศัพท์เทคนิคว่า steady state. So with that condition, what do we have in mathematics? In mathematics, that's go to 0 because things does not change over time, and therefore du dt is 0. dv dt is also 0, and for this continuity equation, d rho dt is also 0. Okay. Next is incompressibility over here. What does that mean? It means that the fluid cannot be compressed to more density. This is not true for gas. For gas, you can have high density and low density, but that's not true for liquid. Now, with the liquid assumption, the rho needs to be constant, okay? So what does that mean in terms of mathematics? If you look at this continuity equation and you think of rho as being a constant, you can take this out of derivative over here. So that's what we get. That's what we get. You take rho out of the derivative, but on the left-hand side is 0. Therefore, the whole thing is 0. We only have what is left is the divergence of the velocity vector is equal to 0. All right. Now, what's next? Oh, before what's next? If I go back and check the mathematical meaning of the divergence, I get that expression over here. Again, because we do not consider the z direction, therefore that term goes away. The next assumption that we are going to use is that assume that there is no gravity, or we ignore the effect of gravity. What does it mean in terms of mathematics? Very simply, this rho gx and rho gy goes away in this assumption. The next assumption is what we call the fully developed flow, or only horizontal flow. We're assuming that the velocity is only in the x direction. That means that the v here, that y component, is always 0, a constant 0 for this y component of the velocity. What that means is here, the v is 0, so constant, therefore its derivative must be 0 and 0. Its second derivative is also 0 and 0. So what we are left with in this second equation is only that term here. Okay, We also have this here that look at this equation of continuity. dv dy is also 0. Why? Because velocity is only in the x-axis. We only have the u, not the v. The v is always flat constant, and therefore dv dy will also be 0. 0. So now we have this simplified version of. I have this message online to see what I get. Oh, okay, and that's from Chanitapa. All right, let's get back to the lecture. So we have this simplified version of this fluid flow. Okay, we usually call the set of assumption. I don't even know how to pronounce this. It's Poiseuille flow. Okay, it's the flow that we ignore the time and only assume it's in the one-dimension flows. Okay. So the last condition that we are going to use to simplify the calculation is this: a no-slip boundary. What happens at the boundary here as the mass of that fluid flow through the pipe? Okay, what happened is that we are assuming that there is no slip. Let me, but I need to look at the camera though. So let me see the camera. Okay, so for example, if my palm here is the surface, I need to make it a little bit larger so you guys can see it on screen. Okay, all right, it's very cute. Okay, so I have this palm here. This my palm here is the surface, the wall of the container, and this object, my fist, is the liquid droplet. It flows. Now, if there is a slip between the interface and the fluid, you go like this. So there is a relative velocity between this droplet and the wall. That is what we call slipping. No slip means that it's stuck only on the surface, not inside the tube. Okay, อันนี้คือเงื่อนไขของการวิเคราะห์เงื่อนไขขอบเขตก็คือว่าตัวผนังของภาชนะกับหยดของเหลวเนี่ยถ้าเกิดมันไม่มีการสลิปหรือการลื่นนะครับมันจะไม่มีความเร็วคือมันจะติดแงกเหมือนกาวเหนียวติดแงกเฉพาะตรงขอบนะครับเฉพาะตรงขอบเป็นเงื่อนไขขอบเขตส่วนตรงกลางมันไม่เกี่ยวนะครับตรงกลางไม่รู้ว่ามันไหลยังไงต้องแก้สมการก่อนแต่อย่างน้อยตรงขอบเนี่ยมันจะไม่มีการเคลื่อนที่นะครับ so with this non-slip condition we transform that into mathematics. Oh, I think I have I may have skipped the steps. Okay, let's go a little bit here. Speed slower. Okay, so with that continuity equation, you have that equation here. 0 is du dx. That is my first equation that I can use to solve this set of unknown. And the next one here, if du dx is 0, I can focus on this term, and therefore that term goes away. It is 0. What about here? The first derivative is 0, and therefore the second derivative is 0. And that I have then the second equation that I can use to solve for the two unknown, the u and the p. Okay, now that's what I talked about, the no-slip boundary condition here. The u at the wall is 0. Only at the wall, at this wall and at that wall. Okay. Now we're at the point where we can just simply do the kung fu mathematics and we get the solution. And we can see then at the end, the solution of how the fluid flow with viscosity. Okay. ถ้ามันมีความหนืดมันจะไหลยังไงแบบไหน Okay.
อาจารย์คะ
Before we go yeah, kung fu. You need to
อาจารย์คะ
yes
คือเราเหลือ2สมการหรือ3อะค่ะ
the where
ตรงกลางด้วย
the why. Okay, so there the question was that do we have 3 or 2 equation? Why am I neglecting the middle equation? Well, you can think of it as 3 equations. That's fine. Um, I counted 2 to make it simple. You can look at the middle equation and see what it means. In this middle equation, the left-hand side is 0. They're all 0. They'll go away. The right-hand side, you only have this dp dy and the minus. Now the minus does not matter. It's not important because the left is 0. So that's what we get. dp dy is 0. What does it mean? It means that the pressure does not change in the y-axis. That's what dp dy is 0 means. D is the change. The pressure does not change along the y-axis. Along the x, it's going to change. You see, because the fluid, the liquid flows from the left to the right. So which side do you think has the higher pressure? Any idea? If it flows from the left to the right, which one has higher pressure?
I think it's towards the end.
I mean the left. If you compare the left end and the right end, and this liquid is flowing from the left to the right, like so, the left to the right. Which end has higher pressure?
Right side.
This region or that region is flowing from the left to the right. So when that happens, the pressure, you can imagine if you have the same pressure both on the left end and the right end, if the pressure is the same, does it flow?
No.
No, it will not flow if the pressure is the same, and therefore, if it flows from the left to the right, which end is higher in pressure? Which one do you think? You go there. Which end has higher pressure? You go left or right? What do you think? What do we have? Oh, bad connection, it says. Don't know what happens. Just ask Paradas if she can figure it out. สมมติว่ามันไหลจากทางซ้ายไปทางขวาฝั่งไหนมันจะมีความดันสูงกว่ากัน
ท่อมันเท่ากันก็น่าจะเท่ากัน
ไม่ถ้าความดันทั้งสองข้างมันเท่ากันมันต้องคงไม่ไหลใช่ไหมครับมันไหลเพราะความดันใช่ไหม
ก็เราทำซ้าย
แสดงว่าทาง ซ้ายมันจะต้องมีความดันสูงกว่าใช่ไหมครับ
อือฮึ
ตรงนี้แล้วก็ทางขวามือต้องมีความดันต่ำแสดงว่าไอ้ความดันเนี่ยมันก็จะต้องต่ำลงเรื่อยๆนะถ้าทางซ้ายมันสูงกว่ามันก็ต่ำลงต่ำลงต่ำลงต่ำลงเรื่อยๆมันก็เป็นฟังก์ชันของ x นั่นเอง so anyway we can think of it as just two equations because the pressure does not depend on y, only depends on x this way. So yes.
I believe our friend Dui is sending message in the group. I think he has sent choice in the group, not this Ajahn, in the group general.
Okay. There's some. Let me see the chat converse. Oh, okay. Now, sorry, Dewey. I need to give you enough. Okay, the right is higher. So Dewey asked Ajahn Krab, the continuity equation also have the generation term. So here we also assume that there is no additional fluid generated in this pipe too. The answer is yes. Okay, very good for asking. Okay, now so we're assuming that we cannot generate additional fluid in this problem. That is not okay, as good assumption, but there are situations that you can have generation term that okay, very good. So let's prepare ourselves to solve this difficult equation and understand the velocity profile of this here. All right. I'll just come through here. I need to, relax a little bit. Change my animation into something more exciting. All right, let's go. So with the first equation, now we only deal with mathematics. With the first equation, I can rearrange all the dp dx to the other side and have that expression over here. You see there? I just have dp dx on the other side. I can move this mu over to the other side. We have instead 1 over mu. So that's simple. So what do we do next? We integrate. The first integration, that's what we get. We integrate, and so on the left, we end up with only the first derivative. Okay, on the right, what do? We integrate with respect to the y variable, only with the y variable, and therefore this term acts as a constant in this integration. Okay, think of it as a constant because we are integrating only with the y variable. So when I do that, I get this form on the right hand side. Don't forget the constant c1 of integration. So what do we do next? We integrate one more time. I get that. From the first derivative, I get the value itself. Okay, what about on the right hand side? If you remember high school, maybe 12th grade, I believe you study calculus a little bit. When you integrate y, what do you get? You get y squared over 2, and also that constant remains there. Integrate this, what do you get? C1 times y, and also don't ever forget this constant C2. So we have this, after a series of integration, you get this final form of the speed of the fluid, of the liquid in the x direction. Now, how do we figure out C1 and C2? Well, we use the no slip condition. You see that from this geometry, the U at this height, U of plus h must be 0. And the U at this height of negative h must also be 0. U is a function of y. Okay. So with that, I can substitute h into this equation. That's what I get. I put plus h there. I have h squared. I have plus h, and then C2 is equal to 0. I can also substitute minus h into the final form. What do I get? I get this h squared. But here is minus. It's minus because this one is proportional to y, not y squared, y. And therefore, you still have minus sign over here. All right. So I get that. I have two equations. I have two unknowns, C1, C2. What do you do next to solve for C1 and C2? What I can do is I can subtract. I can subtract the second equation from the first equation. If I do that, let's take that whole equation minus this second equation. What do I get? Anyone? Let's look at the right-hand side. 0 minus 0 is 0. What about on the left-hand side? The first term are identical for the up and the down, therefore they are 0. The last term, C2 minus C2, you get 0. What about this here? What do you get for the middle term? Anyone? Let's ask Di-Chen. What do you get for the middle term?
2C1H.
Okay, very good. So you have 2C1H is 0, and therefore C1 is, the answer is from Patrada.
0.
Very good, 0. So the answer is 0. What do I get for C2? I simply just substitute 0 here into the first equation. And therefore, C2 is simply minus of this front here. I get that. Okay, very good. Now we have this full information to construct the solution. I put C1, C2 back into the U, and I get that. Okay, and that is the mathematics. That's mathematics, and I don't know what it looks like. To know what it looks like, I go to the graph plotting software, and I do this. I get that answer. Now this arrow is the velocity. It's the U. It's the U velocity. Now notice that if you climb up to this level, to this height, at this height, y is h, therefore the whole thing will be 0. At this depth, y is minus h, and therefore the u is 0. In the middle, you have this different value of the speed. The speed is highest in the middle of the pipe. You go very fast in the middle and getting slower toward the side of the pipe. Okay, and the function is parabola function. Now notice that the velocity u only depends on the vertical. You know, if you look at different location of the pipe, maybe right here, you have the same velocity profile. Okay, so the u, if you look in the x-axis, the u remains constant. U only change along the y-axis in this problem. Okay, So that is how we get the problem. Okay. Now you might notice that we have got only half of the solution. We only know the speed. We don't know the pressure. So what about the pressure? To compute the pressure, we can go back to this equation in the beginning, okay? And then rearrange a little bit. Now I just throw the mu over to the other side. Now I have this mu here, okay, but still the same equation, as you might notice. So what do we make of the pressure? We know that the pressure depends on the x value. Dewey and Patrada said that pressure is higher on the left, and lower on the right, and that's why it flows from here to there. Okay, but what is the value precisely, and what can we do? I can take derivative respect to the x one more time. When I do that, on the left, I get d squared p dx squared, okay, d dx one more time. On the right, that derivative is placed next to the one before, right here. Now the mu is just a constant, that is viscosity constant, okay. What can we do next to learn about the nature of the pressure? Okay. Now look at this derivative here. There is an identity, the mathematical identity of derivative, that you can switch the ordering of the derivative. Okay, in this case, here's what I do. I swap front and back the order of the derivative. I take derivative respect to the x first and the y after. I can do that with this mathematics. Very good. Now you can see where I'm going. Can you see where I'm going? What is the last step for that? If I do this, what do you think is the last step? Once I have that already. Can you see the relationship? If I move my mouse over here a little bit, you know, so you see, oh, from Dewey. No? Okay. Dewey said use the other EQ. Very good. Now, if we go back to here, and you see that the du dx is 0, and therefore the whole thing on the right hand side cancel out to 0, and we only have 0 in this case. So what does that mean? What does it mean when dp squared dx is 0? Okay, it means that the first derivative of the pressure is a constant. And we can translate that into a simple physics sentence, the following, that the pressure drops at constant rate. Okay, for example, if the pressure on the right is 0, perfect 0 Pascal, is difficult to do, but we can imagine that. Let's say on the right of the pipe is 0 Pascal. On the left is 100,000 Pascal. What do you think is the pressure exactly in the middle over here? If the pressure always drops at constant rate, the pressure in the middle will be how much or how many pascals? On the right is 1,000. On the left is 100. On the right is 0. On the left is 100,000 Pascal. In the middle is what?
Exactly 50%.
Sorry, what?
Is it 50% of the right-hand side?
Very good. So it's 50% off. It's like go shopping. So it's 50,000. Okay, very good. So that's what we have for the equation. Now this was very long derivation, but at least it's the first time that you ever see how we solve Navier-Stokes equation. Let me review what we did. Okay, so you get a sense of what we have been through. Okay, we always have two sets of an equation. The first set comes from Navier-Stokes itself, and the second from continuity equation. Now, we may want to apply many assumptions to make the equation easier, but still we need two sets of equation, Navier-Stokes itself and the continuity equation. And when you do the math, you can do integration twice, you get the u. You are going to get this constant of integration, and you need to find that constant using boundary condition. Okay, so we got that C1, C2. We have then the full form, but that is not enough in this analysis. You have to go to some visualization software to plot the graph to see what happens in the actual simulation. Now, in this problem, the speed is faster in the middle and slower on the side of the pipe. Okay, we can solve for the pressure by taking another derivative of this Navier-Stokes, and you get the pressure drop. In this case, it drops at constant rate. Very good. Now, before I show you a brief introduction of how we do it using numerical method, I want to give you an overview one more time that to solve for the motion of the fluid, we need two sets of an equation, the Navier-Stokes, which is really Newton's second laws of motion. And also we need the continuity equation, solve it together. So in actuality, you can't really solve this by hand. You need to use a lot of numerical method and techniques to do that. And to do that, you can use MATLAB. You can use ANSYS, that is the name of the software. It's very popular, ANSYS, ANSIS, or MATLAB. In this software, you can just simply have this graphic interface and you can drag and drop, just like using PowerPoint, very simple. And then you click and you enter the value for the mu, the viscosity factor, enter the condition at the boundary and so forth, and you click, and then it gives you the answer. But that is too easy. I want you to find a time to practice what you have studied just from the beginning of this series of lecture. Do try to read this document, okay? It will give you a nice summary of what you have studied in this series of lecture, okay? So I have this link for you, so let me take you for a tour of this document, okay? So these two researchers are trying to find the flow of the fluid, just like in the heart. In the heart, you have this pumping. So the flow is not steady. That means you have time dependent. But to make the systems somewhat easier to solve, they make this simple model of the two-dimensional flow in this way. It's still two-dimensional, and the width of the pipe is 2b instead. Now here is horizontal, that is vertical, just like what we had in the PowerPoint lecture. Instead of having the pressure constant in time, like in the previous lecture, we have here the pressure P depends on time, just like the heart pumping. You know, that's the P. And the P on the right is assumed to be 0. Okay. So how do we solve this problem? And how do we understand the flow of the fluid inside a vessel, for example? And here we have this equation of Navier-Stokes equation. Now notice that on the left-hand side, we have now du dt. As compared to the lecture, we set that to 0. Okay, if you go back to the lecture, you will see that we set all that to 0 for our simple model of Navier-Stokes. There you go. So in the document, it's no longer 0, but something, but the rest is the same. Now we have this boundary condition that the pressure only on the left wall is not constant anymore, but depends on time, and the time dependence is cosine function. You know, it goes up and down, up and down. Very good. Now we have this equation, and how do they solve for this equation? Which you can go read as a homework problem. You see there, they integrate twice. Integrate twice in the equation number 5, and they then transform the set of PDE into matrix form, just like what we did. Just like what we did in the previous lecture. Let's see, where is it? Where is it? Okay, over here. Okay, in the matrix form. So do give yourself a chance to try to practice your reading skill and your kung fu skill, and you know, play around with the MATLAB code and get the answer. Let me skip forward to the result of the animation of the calculation. Okay, now what we have here in the graph A is the velocity profile of the fluid as how it depends on time. This axis here is the time dependent, and this vertical here is the u, the speed. Now, if you look at this animation, as the pump occurs, you have the speed just like the heartbeat. Now, they can use this equation to build artificial heart. It's very hot ongoing research nowadays, so you can try to read more about this and what happens to the solution of the problem. Okay. Now, what we have talked about so far, of course, is not going to be extensive as you would hope in the actual CFD courses. CFD means computational fluid dynamics. It's a huge field in engineering and physics that talks about how you simulate the flow of fluid using Navier-Stokes and continuity equation and all kinds of other auxiliary function. Okay, but at least I think I have given you some of the introductory feeling of what happens when you deal with Navier-Stokes and continuity equation. Okay. Now, sadly, it's pretty much the end of the series of this lecture because the semester is ending and the COVID curfew is ending for Thailand also. Okay, so I guess it's time for us to stop worrying about the academic or Vishagan in Thai language for a while and go travel, go places, have a nice vacation instead. So it's time for vacation. That's what I'm saying. Okay. I don't know if I'm gonna have time to put on another series of lecture within this year. Maybe next year I will have more time to do this, but let's say that see you next time with the wave equation. All right. Any other questions, if you may? Maybe Dewey cannot talk somehow. I will check the chat message if I can.
Mine is not related to the lesson that Ajahn have covered. I just want to request Ajahn whether there is some book or reference where we can look into Taylor expansion in 2D and 3D.
Oh, I would recommend you. I would highly recommend you to start with Wikipedia. That's what I do all the time. But only start with Wikipedia. In that you can dig through the online book but I don't know off the top of my head.
It's quite expensive. There is no free, but I just browse and it's quite expensive.
Oh, okay. You want extensive?
No, I don't want expensive. I was just thinking if Ajahn has, I'll borrow and return back after a month. My friend wanted that.
Yeah, I do have it. I have the book. I have the book in my office.
Okay, Ajahn. So, related to Taylor expansion dimension?
Yes.
Okay.
In many dimensions.
Oh, it would be great.
Have you looked at the Krasik engineering book? Is it in there?
Oh, yes, Ajahn, but we have to purchase, I think. It's not open.
The Krasik is in the library. You can go in the library. There are 5 copies of that in the NU library. You can check it out.
Okay, Ajahn.
Okay.
Thank you so much.
What about the what about the Thai students from Phitsanulok? Do you have any comment that you want to add before we end this long journey of mathematical methods in physics for a while? พักไว้ก่อนเดี๋ยวเทอมหน้าเจอกันใหม่ปีหน้าเจอกันใหม่
Today is last day really oh
yes today I think we don't have any more time I hope that I can slow down the time I can go back in time and teach you once more but sadly I can't so today is the last day of class. Any comment do you want to add? Anything you want me to change and improve so that your friends, your other students can benefit from the changes that I make. ต้องการให้แก้ให้เปลี่ยนตรงไหนบ้างไหมเอ่ยเทอมหน้าน่าจะมีเวลามากกว่านี้เพราะผมก็จะไม่ได้ขาดอะไรมากมายแถมบางทีให้ไปดูเองด้วยซ้ำก็จะมีเนื้อหาอย่างอื่นที่เพิ่มขึ้นมาให้มันเต็มนะครับส่วนอันที่มันอัดไปแล้วทั้ง 4-5 เลคเชอร์ก็จะไม่ได้มาสอนสดนะก็จะให้คุณไปอ่านเอาเองหรือไปดูเอาเองนะครับแล้วก็จะได้เนื้อหาเพิ่มมากขึ้นมีเวลาสัก 1-2 นาทีคอมเมนต์ไม่เอ่ย
อยากคอมเมนต์ค่ะแต่ยังนึกไม่ออกค่ะแต่ว่าสอนดีอยากได้แนวการเรียกว่าอะไรนะคะแบบว่าปลูกฝังความคิดแบบที่พาคิดตั้งแต่เรื่องแคลคูลัสอะไรอย่างเงี้ยค่ะแนวนั้นจะดีมาก
อ๋ออยากให้ย้อนเวลากลับไปพูดเรื่องแคลคูลัสตั้งแต่ต้นก็น่าจะได้นั่นมันก็เป็นไปได้นะครับเพราะว่าตอนนี้เรามีวิดีโอที่เป็นแบบ advanced ปลายทางไว้ก่อนแล้วเพราะนั้นเทอมหน้าผมก็ไม่ต้องมาทำตรงนี้อีกเทอมหน้าคนเข้ามาดูเขาก็คงจะได้เห็นโอ้นี่ไงพี่ทัศรดาเป็นอย่างนี้นี่เองประมาณนี้แต่ว่าพอเขามาดูผมก็จะเพิ่มเนื้อหาตั้งแต่ต้นทางต้นน้ำแล้วก็จะมีกลางน้ำส่วนตรงนี้ก็จะเป็นปลายน้ำที่อัดไปแล้วจะให้ไปดูเองเห็นไหมในวิชาแอดเมตอดตรงนี้นะครับ
อาจารย์ก็ยังสอนออนไลน์อยู่เหรอคะหรือว่าตัดวิดีโอ
อ๋อก็คิดว่าคือเขาจะให้สอนออนไซต์แล้วนะเขาจะให้สอนออนไซต์แล้วแต่ว่าก็ยังจะต้องยังจะอัดวิดีโออยู่ก็ไปสอนในห้องไปสอนในห้องเรียนแต่ว่าก็ไปอัดตัวในห้องเรียนนะครับแล้วก็จะมีกล้อง2 ตัวกล้องตัวหนึ่งก็จะฉายไปยังผู้ชมดูแบบว่ากระหึ่มมามากน้อยแค่ไหนนะครับประมาณนี้โอเคแต่ยังจะให้มีออนไลน์นะครับเพื่อประเดี๋ยวแฟนคลับจะรู้สึกว่าห่างเหินกันไปนะครับโอเคคุณดุยก็คงจะได้ส่งมาแต่ข้อความนะครับ Just wondering where did you derive the additional stories from it rhymes with the contents very well I don't understand the meaning of that Just wondering where did you derive the additional stories from? It rhymes with the contents. I meant the size equations. The side equation. I'm not sure what you mean there. Okay. The way you derived which side equation? I mean, there are so many equations. Which slide? Number 9? Are we talking about number 9? We're talking about number 10? 10 here? Or 11? Which one? Which slide are we talking about? The recent one. 11. I didn't derive the side equation. The pressure? Talk about the pressure. Maybe there's a lag time between Thailand and Japan. That's why it's somewhat difficult to exchange idea back and forth. I wonder if I can have better internet connection. Okay. Anyway, I'm not really sure what you mean when you say it rhymes with the content very well. It's like I'm writing a poem or something, but I'm gonna go with the heart here. Okay. Oh, okay. Okay, very good. Well, you mean the way I deliver and narrate the stories. Very good. So maybe it's just the way how I see things. The way I see physics is that I see it as a story. In each lecture I have a story to tell, And a story begins with a climax. See, I always have this climax of the last lecture, always. And then I prepare the first slide one by one to lead to the final lecture and the final slide. That's how I prepare it. Okay, and I think it's kind of fun to see things in the coherent and a compact story. Very good, because I think it's interesting that way. All right, so I guess it's time to say goodbye, and with you know, a sad song, but an ending goodbye. All right.
Thank you so much, Ajahn.
Very good. Hope to see you again in some social media or something. All right. I'll see you next time.
Thank you so much, Ajahn.
See
It
you.
is great pleasure learning from you.